Hey listeners, this is Pradesh Chaudhary Quantum Guru. I am going to present you a very good problem of rigid body dynamics in this video. This problem involves two concepts. One is the conservation of mechanical energy and the other is the main concept that I want to emphasize on this video, that is the how to calculate angular acceleration of a rigid body performing CTRM. So let's go into some conceptual part before we go and solve this problem. So the first thing we need to learn, suppose we are given a rigid body and we are given its angular acceleration, angular velocity and acceleration of any point, say A, and we have to find the acceleration of any other point. So this is a body performing CTRM and A is a point of this body whose acceleration is AA vector, and we have to find the acceleration of any other point, say P, which is at a distance r from A. So we know that in rigid body the path of any particle as seen from any other particle in planar kinematics is circular. So with respect to A, the path of P is circular. So the circle, the center of the circle would be at A. So with respect to A, there would be a centripetal acceleration r omega square. One acceleration would be tangential acceleration r alpha, and then to get acceleration of P with respect to ground, we have to add the acceleration of A, that is A. So acceleration of P would be the vector sum of these three acceleration. That is a very important first part. So now body is performing CTRM and we wish to find its angular acceleration. So obviously to find angular acceleration alpha, we have to apply torque is equal to I alpha. Now the question is that can we apply torque about any point? So answer is yes, you can apply torque about any point. But before applying torque about any point, say A, we have to see that whether it is accelerated or not accelerated. So if it is accelerated, so basically you are sitting on a non-inertial frame, you have to apply pseudo force in addition to real forces at the center of mass. So here this is a rolling body. The body has a acceleration center of mass is acceleration A, angular velocity omega and angular acceleration alpha. Two forces F and Fs is friction, are acting. Weight normal have no net effect in terms of neither in terms of acceleration nor in terms of alpha. So these are the forces, and we want to find angular acceleration by applying torque about A. So we want to apply this equation, torque about A is equal to I about A alpha. Remember, you can apply torque about any point, so alpha would be the same. So tau A would be different and so would be IA. So here IA is the moment of inertia about an axis passing through A and perpendicular to the plane of motion. So first find the acceleration of this point A, like we just discussed. So with respect to center of mass of the body, the one acceleration would be centripetal r omega square, one acceleration would be tangential r alpha, and in the ground frame we have to add the acceleration of center of mass A. So net acceleration of this point A would be vector sum of all these three. Now torque about A, in addition to torque due to these forces, we have to add the torque due to the pseudo forces. The pseudo terms, because of this acceleration, torque force would be pseudo force would be mr omega square. Because of this term, pseudo force would be mr alpha, and because of this A, pseudo force would be ma. And now we can apply. So if we can incorporate torque due to these pseudo forces about A in addition to these forces, and also write the moment of inertia about A, you will get the same answer. But this will make our life tougher because first of all, moment of inertia about A would be difficult, not tough, but it will involve more steps, and so will be the pseudo torque terms, right? But technically we can still get the same answer. And then can we apply torque about center of mass? Yes, we can apply torque about center of mass. So suppose we want to apply torque about center of mass is also accelerating. So if we sit at the center of mass, we have to apply pseudo force, but pseudo force is applied at the center of mass. So I want to apply torque about center of mass. Torque Cm is equal to ICM alpha, and then we have to put the pseudo force at the center of mass itself, and we are calculating torque from the center of mass, so this pseudo force torque will be 0. So that is the simplest thing, and also ICM is easiest to calculate about the center of mass, right? And now the next thing is, can we apply torque about IOR? Again, yes, you can apply torque about any point. So here we have to we want to apply torque about IOR is equal to I about IOR alpha. So once again we have to see what is the angular what are the various terms of the acceleration of IAOR. So with respect to center of mass, one acceleration would be R alpha and one would be R omega square, and in the ground frame we have to add A. If it is rolling without slipping, or even if I am saying this is IOR, that is enough to say. So this point has a 0 relative velocity with respect to surface, so A and R alpha must be matched, must be equal. So net acceleration would be R omega square, right? So now I want to apply torque about IOR, so I have to put a pseudo force. Net acceleration is R omega square, so pseudo force at the center of mass would be M R omega square, like this. And you can see that this pseudo force line of action is going towards the IOR about which we want to calculate torque. So that torque would be 0. And other benefit would be that by applying torque about this point, the torque due to friction and normal will also be 0. So in this case, this would be the easiest. But there would be problem. Suppose we attach some more mass here, so that the center of mass is not here, right? Center of mass is not here. Center of mass can be somewhere here. And then the line of action of the pseudo force always passes through center of mass, like this. Then line of action of the pseudo force will not pass through IOR. Then there would be a pseudo torque term when we calculate from IOR, like. And the problem that I am going to take, that will take these points. So that's why that question is very good. All right. So now we can proceed to solve the question. So this is the question. So you can see in this question, this is a ring. This is a ring of mass M. All right, and radius R. And this is a small block of mass M. This block is rigidly attached. So this is rigidly attached, and the angular position of this mass at from the upward drawn vertical is theta. The system is released from rest at theta is equal to 0, mean from the upward vertical. Surface is sufficiently rough, mean it will always roll without slipping, and we gave a gentle push so that it start rolling. And when theta becomes 90, mean this block P, and this body P reaches here. At that moment, we want to calculate the angular velocity of this system, angular acceleration and friction acting on the body. All right. So we start from this position. In this position, this mass was at the highest point, and we gave a gentle push. And now it has reached to this position, and the center of the ring has got a velocity v, and the assembly got angular velocity omega. Surface sufficiently rough, no slipping. So friction acting would be static friction. This surface is fixed, so the point of contact has a 0 velocity, so friction work is 0. Other forces, mg normal, mg conservating, normal is not doing any work, so mechanical energy of this system is conserved. So applying conservation of mechanical energy from this state to this state, and also at this moment, because it is rolling without slipping, so velocity of the center of the ring and angular velocity is relation v is equal to r omega. This mass will have a velocity r omega with respect to the center of the ring, and in the ground frame we have to add velocity v also. So the net velocity of this mass would be root 2 r omega also, or root 2v. So apply conservation of mechanical energy. Loss in potential energy is equal to gain in kinetic energy. The center of ring moves on the same level, so its potential energy does not get lost. This mass has come down by a distance r, so its loss of potential energy is mgr. gain in kinetic energy of this ring, it is doing CTRM, pure volume. So its kinetic energy will have two terms, half m VCM square plus half I Cm omega square. So half m VCM square would be simply half mv square. ICM is equal to mr square, omega is equal to v by r. So half ICM square will also be half mv square. So total kinetic energy of the ring is mv square, and the kinetic energy of this mass is half m into root 2 v square, and that is total gain of Ke, and this is the loss in P. So just simplify this thing. So you will get V is equal to root 2 gr by 2, and omega is equal to v by r. So omega is equal to square root of g by 2r, and that's the angular velocity. The first part we got, and this part would be used in the latter part also. So one more thing, this omega is equal to square root of g by 2r. So just rearrange that. So you will get r omega square is equal to g by 2. And now I want to calculate angular acceleration. So for the calculation of angular acceleration, I want to apply torque about the IAOR. So this is IAOR, and the center of this ring has acceleration A, angular velocity omega of the whole assembly, angular acceleration alpha, no slipping. So A is equal to r alpha, and we just obtained at this moment r omega square is equal to g by 2. So acceleration of the point of contact with respect to the center, that is r alpha, and towards center r omega square, and we have to add acceleration A. From no slipping condition, A and r alpha are matched, so the net acceleration would be r omega square, and that r omega square is equal to g by 2. So acceleration of the point of contact with the ground has a acceleration g by 2 towards center of the ring. And now once again this picture, this is a mass m, this is a mass m, and the center mass is here. This is r by 2, and this is also r by 2. Other forces acting are the weight mg, this weight mg, normal, and friction. So we want to apply torque about IOR, so we have to put the pseudo force at the center of mass. So the acceleration of the point of contact is g by 2. So at the center mass we have to put a pseudo force, net total mass, into acceleration the opposite direction of the acceleration of that point. So here the pseudo force would be 2m into g by 2. So 2m into g by 2 is simply mg, and now we can easily calculate alpha. Alright, but before that let's calculate the moment of inertia about IOR. So this ring has a moment of inertia about center mass mr square. So moment of inertia about IOR would be mr square plus mr square, that is 2mr square. And this point is at a distance root 2r. So its moment of inertia would be m root 2r whole square. So moment of inertia of the ring is 2mr square, and this mass has a moment of inertia m root 2 whole square, and add these two you will get 4mr square. Now torque about IOR alpha is equal to I about IOR alpha. So I about IOR is 4mr square, alpha is alpha, and torque about IOR. So three torques get cancelled. This mg, n, and fs, three forces torque has cancelled because their line of action are passing through IOR. The only torque is because of this mg and this mg. Torque because this mg is mg into r by 2, and torque because of this mg is mg into r. They have same sense in the direction of alpha. So net torque is 3 mg r by 2, and just simplify this, we'll get alpha is equal to 3g by 8r, and a is equal to alpha by r. A is equal to r alpha, that will be 3g by 8. So we have very easily calculated angular acceleration about IOR in this case. Now we want to apply torque about center mass to get the same result. Alright. So once again this is the picture. At the shown moment, center mass has acceleration A, angular acceleration has got omega is equal such that r omega square is g by 2, no slipping, so A is equal to r alpha, and r omega square we have calculated g by 2. So we want to find, because we want to apply torque over center of mass, so first we have to find the acceleration of the center of mass, and the center mass is here exactly in between the center of the ring and this mass. All right. So with respect to the center of the ring, it will have a acceleration r by 2 omega square, right? And that r by 2 omega square will be g by 2, because r omega square is g by 2, is actually g by 4. And one acceleration with respect to the center of the ring would be r by 2 alpha. R alpha is a, so that is a by 2. In the ground frame, we have to add acceleration a also. So net acceleration of the central mass is the vector sum of these three accelerations. And now we want to draw the FBD. So in the FBD, obviously weight of the ring would be there, normal reaction would be there, weight of that rigidly attached body would be there, and a friction would be there. So, and this is my x direction, this is my y direction. So first we want to apply equation for the translation motion. F external is equal to MACM along x direction first. This is x direction, so net force along x direction only Fs, and Fs, this is Fs, and in place of m we have to write the total mass m and m, that is 2m, and net acceleration along the x direction of the center mass, this is a minus g by 4. So this is our first equation. Fs is equal to 2m into a minus g by 4. Similarly, we have to write the equation along y direction. F external along y is equal to total mass into ACM along y. So y I have taken downward directions. Along the downward direction, the net force is 2 mg minus n. And acceleration along the downward y direction is a by 2. So equation is 2 mg minus n is equal to 2m into a by 2. These are the translation motion equations. And now the equation of the torque about center mass. So you can see that this torque, because of this mg and this mg, would be cancelled because they are at the same distance and the value same, senses are opposite. So torque would be only because of n and fs. Alpha is in this direction. So n torque is in the direction of alpha, and fs torque is opposite to direction of alpha. So torque of n would be positive and torque of fs would be negative. So I alpha about center mass is torque about center mass. So first we'll calculate moment of inertia about center of mass. So moment of inertia of the whole assembly about center mass. So moment of inertia of the ring about its center is mr square, plus this is r by 2 distance, so we have to add mr by 2 square more. And this point has this body has also moment of inertia about the center mass is mr by 2 whole square. So overall this is the moment of inertia. And torque about center mass is n into r by 2 minus fs into r. So this, just add these all these terms, so we will get I think mr square, 3mr square by 2. So here 3mr square by 2 alpha n minus 2 fs r by 2, and just multiply both side by 2, you will get 3m a n minus 2 fs. Here 1 r would get cancelled, in place of r alpha I have written a. And now we have got all the equation, just we have to rearrange to solve. So bringing back these two equations were from the translation motion, and this is from the torque. So I want to first eliminate fs. This n minus n and plus n will get cancelled. So if I multiply this equation 1 by 2 and add with equation 2 and 3, so we'll get this 2fs minus 2s will get cancelled, minus n and n will get cancelled, will remain with 2mg. And on this side that will be 4ma minus mg, and that is just ma, and this is 3ma. So take this minus mg on that side, you will get 3mg, and this is a 4ma plus 4ma 8ma. So a we will get 3g by 8, and a is 3g by 8, so alpha is equal to a by r, that is 3g by 8r. And we can put this value of a in the first equation. F is equal to 2m, a in place of a, put 3g by 8 minus g by 4, just rearrange and you will get the friction is equal to mg by 4. So I have shown that you can apply torque about any point, whether a center mass, whether IOR, or for that matter any other point, you will get the same result. Just you should be very clear in calculating the torque due to pseudo forces also, so no problem will ever come. Thank you.